All right, I think we can start off now. So welcome to another one of ASEG's pretty neat webinar series. This one in particular is hosted by Western Australia, and it just so happens that I'm your host, MC Todd Majeski, and I'm the local president here in WA. But our talk is by Ankita Singh, and her talk, as we can see on my slide there, it's Grayscale representative elementary volumes, an innovative approach to investigate pore-scale REVs from raw micro-CT images. Now, before we get to that, though, I do have to do some proper housekeeping. And one of them is really pretty darn important, and that's we really would like to thank our corporate sponsors. And these help us an awful lot. They give us support on so many things, including these webinars, but so many other things too, like the conventions and things, and locally. So our Corporate Plus members, high size, total seismic, and bill size, do quite a bit. And however, we also have corporate members, which again go across all Australia, Southern Geoscience, Santos, and a new one, Transparent Earth Geophysics. So thanks to all of them. And then we do have a massive amount of good sponsors, as you can see, especially in WA, but there's quite a bit in SA and NT, and also New South Wales. Being from WA, I'd like to personally thank all of the sponsors that we do see on this screen, but I'm not going to be able to go through them. But anyway, thanks a lot. And they do help us all over in many different ways. Now, back to what I was saying about housekeeping and Zoom etiquette. Since this is not a presidential debate, we don't want you shouting questions at Ankita or myself, so we'll be using the screen, and you can type in under the Q&A button, you can type in your questions, and at the end we'll review them and hopefully get through all of them. We've got a few upcoming webinars. This one is the most recent coming up, and that's the 21st on Wednesday. And Peter Hatherley has got something pretty neat. It's he's got a LiDAR type talk that's where he's been mapping stranded stream channels in the Lapstone structural complex right near Sydney. So that should be a pretty cool talk. At any rate, we'll continue on. And we do have something, ASEG we're talking about, but we've got a lot of member benefits. So let's go through the list here. Definitely one of the neat things is that we have a nice technical journal, Exploration Geophysics, where we have research and case studies, and not just from Australia, but we try to select the best from all over the world too. We have our own kind of chat rag magazine preview, where we get up to date what's going on across exploration geophysics across Australia. And naturally, if you're a member, you're going to get a reduced entry to our national conferences, and also free entry to the regular technical events in your state, which essentially allows you into this really nice webinar that you see for free. And you do have access to job advertisements, which in these trying times, that's pretty nice to be able to do. And if you've got the cash, we do have annual wine offers, and ours has just gone out. And I've availed myself of that before. You get some very excellent wine for a very good price and delivered to your door. Along that line, assuming that, the COVID restrictions are relaxed, there are always social events that go on state by state. And naturally, this is essentially a professional networking system. So that's going to be helping everyone with that. And we do research funding and travel scholarships for students. In fact, WA's scholarship, travel scholarship applications has just ended, and we'll be reviewing the applicants. And then next year, they will have a good chunk of money to travel to the AGC in that case. Along those lines, one of the neat things I think, very few organizations do this. We offer free membership for students and half price for retirees and recent grads. But that means if you know anybody that's interested in geophysics, geology, physics, blah, 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 you know, just let them know that they can apply and get in for free and get all these benefits just like that. That's pretty cool. All right. So we were talking a little bit, AGC. Well, it's going to be in Brisbane. It's going to be in Brisbane next year, mid-September. And if you notice, the deadline for abstracts now is, we've only got a month. So make sure that you go ahead and do yours so that you can get there. And, you know, we'll assume that it's going to happen. You can see the location there on the website, or you can log into our website and find it. In terms of that, well, yes, we have an ASEG website, as you know, and we send out monthly email newsletters, and more often than that, quite often, we're on Facebook, we're on Twitter, and actually LinkedIn. And one of the other things I think is pretty fascinating is ASEG has its own YouTube site, and what we have there are most of the webinars and a lot of the technical talks that we've given are out there for you to peruse at any time. So you can, if you want to review something or you missed something you wanted to see, you've got the chance. So, okay, there's that. So with that, pretty much ready to introduce Ankita Singh. She's a University of New South Wales student, and you can see her talk there. Grayscale representative elementary volumes, an innovative approach to investigate pore-scale REVs from raw micro CT images. And then we'll just read what I've put here, if I can get, let's move this stuff out of the way so I can read along with you. So she's a PhD student at the School of Minerals and Energy Resources Engineering at UNSW in Sydney. Her work focuses on implementing texture analysis techniques for rock characterization by directly using raw X-ray images. Her PhD work has been published in journals such as Water Resource Research and Geophysical Research Letters. Now this is pretty cool. She's won the Best Engineering and Environmental Student Paper in AGC last year in Perth, and 2019 was a finalist at the UNSW 3-minute thesis competition, which that sounds pretty neat. I mean, I've never heard of anybody able to write their thesis in 3 minutes, but apparently she was a finalist for that. But at any rate, what that's telling us is this should be a pretty good talk. And with that, I'm going to pass everything back to Ankita.
Yep. Right. Sure. So, can you see my screen now?
I can, sure.
Okay, great. So thanks, Todd, for the introduction. And hello, everyone. Thank you for attending my talk today. Today, I'm going to talk to you about how can we estimate the size of a representative elementary volume at pore scale using micro-CT images. So this research has been published in Geophysical Research Letters, and here's the paper. It was just published back in July. I've given here the link to the paper, the data set that was used in this, and also the code that's hosted on GitHub. This is in case anyone wants to read the paper after this presentation and reproduce the code, reproduce the results that I've presented here. So without further delay, I would like to begin the presentation. So porous meteor rocks, these rocks have been studied for a long time now because of their wide applications in CO2 sequestration, in geothermal systems, and in hydrocarbon recovery. Now, these processes happen from a very small scale to a very large scale. And if you really want to understand how does the CO2 sequestration occur, you need to understand how does the CO2 flow in the rock pore spaces. For the geothermal systems, you might want to see how the hot water flows through granites, and fractures in granites. And for the hydrocarbon recovery, you want to have the best possible scenario so you can have the maximum recovery. Now, in order to be able to do that, you need to make sure you integrate across different scales, which is what I mean. What I mean to say by that is, if these processes occur at pore scale and they go all the way, to the core plug, to the well test, to the reservoir thickness, and all the way to the reservoir scale. And when you simulate flow through these rocks at different scales, there are different physical processes that are involved. And it also depends on the heterogeneities of the rock that are involved in these scales. So when you're moving across scales, specifically from the pore-scale model all the way to the reservoir scale, where the transition is almost on the order of magnitude of 10 power 9, the question we must ask ourselves is that, are the rock properties at every scale representative? And that's what is going to be the focus of the talk today. So when I talk about integration across different scales, our focus remains the pore-scale model, which is the one you see here. Now, first let's define what an REV is. An REV is a volume that's large enough to capture heterogeneities of the sample at that scale, and it's dependent on the property you're measuring. So here's an image that shows the REVs that we can get at different scales. On the x-axis, you have the length scale, and you're measuring the property, which is permeability. You can see that there are three different REVs: pore-scale model REV. So the laminar REV is also the pore-scale REV. You have the lithofacies model and its corresponding REV, and then you have a geo model and the corresponding stratigraphic REV. So we focus here on the pore-scale model. And what you see here is that when you're at a really small length scale, you have a lot of these microscopic fluctuations. And you want to get past these fluctuations and reach this region of plateau. And this is when you've reached your pore-scale REV. Now, again, if we zoom in and see what these fluctuations look like and why do they occur, what we see here is that here's your rock. All the purple area is your pore space and your gray area is your rock. And so if you're looking at a really tiny part of the rock, you see that you're only capturing the pore space. And that's why, for example, if you measure the porosity of just a pore space, it's almost 100%. So that's why you have a really high value here. And then as you grow it, you'll see you're incorporating more grains, and then you see the fluctuation until you reach the full size is when you reach the plateau or the REV. And in this study, the rock sizes that we use are of the order of millimeter to centimeter scale. So you can see here, these are the different kind of rocks. For example, this is a Bentimer, this is a leopard sandstone, and these are some carbonate rocks which were fractured. You can see that they are pretty small just by the length of this 50 cents point. And so this is what we're going to study today. Now, in order to understand what happens at the pore scale, we need to understand the digital rock physics workflow. And the workflow basically has three main steps. That is acquiring the raw X-ray images, then carrying out the segmentation, and the last one is to carry out flow simulation, where you calculate all your petrophysical properties such as porosity and permeability. And here are the rocks that we're going to use. So how do we acquire these 3D raw X-ray images? We use a micro-CT imaging facility. The CT stands for computed tomography, or X-rays. And this is the setup we have here at UNSW. And the cool person here you're seeing is Amalia, who does a lot of the X-ray imaging for us. And she's a laboratory manager here. So this setup basically shows an X-ray source. You have a sample which rotates, and then you have a detector. So what this does is that as the sample rotates, your X-ray gives out projections detected by the detector, and these are 2D radiographs, so 2D projections. You then use a reconstruction algorithm to give something that is a 3D representation of your rock volume. So here's example of three rocks. One is a sandpack, which is artificial. Then you have a fieldstone, and the last one is a carbonate. With what you're seeing here are these are the gray level intensities, as we call them. And these values are dependent on the density of the rock material that is encountered by the X-rays. So every voxel in this 3D image is a grayscale value. And so what you see here, for the case of sandstone, which is very homogeneous in terms of the gray level intensities, you see that you have the pore space in black, and you have the light gray quartz. In the case of fieldstone, you can see there's a lot more variation when compared to sandpack. And here you see the darker gray are the quartz sandstone, is the quartz, and the darker black stuff are the pores. These light minerals are glauconite, and you also have iron oxides that are not really visible in this image here. Something that's quite different from both fieldstone and sandpack is the ketone carbonate here. And this ketone carbonate has calcite as its as a majority phase. You again have the pore space. But what's different in this is that you have sub-resolution porosity here that you can see, and often it so happens that the resolution of your X-ray is not enough to resolve it completely so that you can understand what these features look like. So this is the kind of variation we see in terms of the digital rocks. And if we really want to understand what kind of distributions we see for the grayscale values, we plot a histogram. And the histogram looks something like this. So on the x-axis, you have the gray level intensities. On the y-axis, you have frequency. And you see there are these two modes, one representing the pores, which are the low gray levels, and the higher ones are quads for the case of sandpack. And then you have, for the case of fieldstone, you again have pores, quads, and this third phase that slightly shows up here is the glauconite. And the empty spaces here are actually represented by the iron oxides that are not very frequent. With the ketone carbonate, we again have the pore space. The second peak here represents the calcite. And if you see that there's an elongated region here, which might not seem obvious from the histogram, but you know that there is porosity in these grains here. And so that's what is shown in the histogram. So once we've acquired the 3D raw X-ray images and we've visualized it as a histogram, what we do next is we carry out segmentation. The segmentation is simply identifying distinct phases and assigning it a particular value. And we do that by choosing thresholds. So you could choose threshold T1, T2, T3. And what that would mean is that if I choose a threshold of T1, everything below it is assigned the value 0, which represents a pore space. And everything higher than that is represented as grains. And so that's why you see these two distinct phases in all of these images representing pore space and the solid phase. You could have more than one phases. That really depends on the analysis you're doing. And the reason why I tell that you can choose T1, T2, or T3 is because this segmentation really depends on the user expertise and the type of algorithm that you're using, and which might give slightly different results as well. But at the end of the day, what I'm trying to get to you is that once you get the raw X-ray images, you segment them to separate the phases. And you do this so that you can then calculate permeability, porosities, using flow simulation. You need flow simulation for permeability, but obviously porosity is a very straightforward calculation. So that's what the digital rock physics workflow looks like. Well, it might seem straightforward and you can go on a holiday very soon, but what if somebody told you there are actually more pitfalls than it's actually seen here? And when we look at the pitfalls, we can identify them at several stages as we go across the workflow. So let's look at the first one, which happens when we go from acquiring the 3D X-ray image to the segmented phase. What are we losing when we move from step 1 to step 2? The first thing is that when we binarize the image, that means we go from here to here, we have lost all the textural information of the rock. We have lost all the spatial variation that might be able to tell us what are the different features, what are the mineralogical heterogeneity, how well are the pore space connected, because the T1, T2, T3 can give us different results. And another reason is that we might miss the microporous region if we do not have high enough resolution. And if we are not able to capture these vital information when we are going from the X-ray images to the segmented images, we might not have a representative structure of our rock, of our rocks. And the second thing that might play a role is the fact that these flow simulations are computationally expensive, and they are really time consuming. You might get away if, you really have just one one value of permeability that you need to calculate. But if you have to do an REV analysis where you need a lot of permeability values at different length scales until you reach the REV scale, it takes a lot of time, and you need really good high performance computers. So in the light of that, how credible is our REV analysis when we have uncertainties from so many areas? What are we going to do? And so that's why the motivation of the talk today is to provide an objective perspective to this whole analysis that is currently driven by the digital rock physics workflow. We want to be able to see if the lost information regarding the texture of the rock, including the mineralogical heterogeneity, the connectivity of pores and minerals, or the microporous region, on the whole, the spatial variation of these pixels, can we still withhold those these information and not go the segmentation path. And in fact, in a review paper by Wilden Shield and Shepard, this challenge has been discussed, where when we have a lot of sub-resolution information and we lose this information because of the segmentation procedures, because we are literally binarizing the image, can we do something about it? And that's where the grayscale image analysis, or using the raw micro-CD images directly, becomes really important. So having said that, I will quickly have you guys run a poll. Lauren, would you mind getting the poll out? What we're going to do is imagine that you're blindfolded on a sinking boat, right? And a savior shows up who can lend you a rope and pull you to the shore. But you must choose rope 1 or rope 2. But there are certain conditions. The savior tells you that one rope is, let me just show you the ropes. Here are the ropes. So that's rope 1 and that's rope 2. The savior says that one is a polypropylene rope and the other is a manila rope. So for those who don't know what a polypropylene rope is, it's a rope that is used to bifurcate the swimming or create swimming lanes. And the manila rope is the one that you use in tug of war. So the savior tells you these are the two ropes. He doesn't name which one is which, but he says he has one polypropylene and one manila rope. He says, you can't ask me what it is. You cannot wet the ropes to assist in identification, and you can't burn the ropes either. So these are the conditions. So what will you do to identify the rope type? 1, you would wet it anyway and discard the rules. 2, you would swim to the shore, and that's preferred. And you would identify the type of the rope by feeling it, or you would prefer to sink. So I think Lauren's got the poll out. If everyone can just vote, yeah, that would be nice.
Yes, the poll is launched for everyone.
Yep, that's great.
Okay, so up to 44% have voted. So it's 11 out of 25 people have currently voted. So we'll just give everyone a little bit more time to pop their answer in.
Sure.
Okay, we're up to 17 out of 25 have given an answer. Would you like me to end the polling or continue it for a bit longer?
Yeah, let's end the poll. That's
okay,
fine.
no problems. I'll launch that for everyone to see the results.
Okay.
Okay, it should be on everyone's screen now.
Wow, I'm surprised that no one preferred to swim to the shore. That's the easiest way. Okay, yep. So you could identify by sinking it in the water, which is a little dangerous if the savior decides to not save you. By sinking in the water, you will realize that the manila rope might get wet and will not withhold the weight. And so you might not want to choose that method. Now, when you identify rope by feeling it, which I'm happy is a majority, what would happen is rope 1, when you touch it, you would feel it's lightweight, it feels soft, and it's like velvet. And that's what your polypropylene rope feels like. When you talk about the manila rope, it feels rough and it feels scratchy because of the materials it's made of. It's made of natural fibers. And what you're really doing by analyzing or feeling these ropes is you're analyzing its texture. And so this is what we're going to do. So texture analysis is something we've all encountered, and we've even used it. And as it's defined, texture analysis is a way to describe some things that are rough, smooth, silky, bumpy, and you do it as a function of the spatial variation in the pixel intensities, which is how you feel the things or how rough things are. And these techniques have had great success in medical imaging, in remote sensing, mineral identification, seismic analysis. And so now we're going to apply it to porous media rocks, which have not seen as much of the texture analysis being done in that specific area. So the texture analysis that we are going to carry out using the method called the gray level size zone matrix was initially developed by Thibault in 2009, and he used this technique to classify cell nuclei and to differentiate which is a homogeneous versus a heterogeneous nuclei. And on your right hand side, what I've highlighted is why are we doing what we are doing, and how are we going to address all of these challenges, and that's using the texture analysis. So let's first look at how do we calculate the gray level size zone matrix. Right, so this is your grayscale image, and here are the numbers that represent this grayscale image. The first thing that you do when you want to make a gray level size zone matrix is that you identify how many unique gray levels you have here, and you put them down as your rows. So you have 1, 2, 3, 4, and you have 1, 2, 3, 4. So these are your unique gray level intensities, and it's a fixed number depending on the number of the intensities you have in your image. Now there's another term called the size zone. This size zone calculates how connected is the gray level value 1 to itself. It might be isolated, it might be connected to another 1, it might be connected to 3 ones. How is it connected? So for example, if we look at this gray level intensity 1, it occurs as a size zone of 1 3 times. I'll repeat that again. The gray level intensity 1 occurs as a size zone of 1 3 times. And the reason why that happens is that you see there's a 1. In the neighborhood, there is no 1 here. So that's an isolated. Again, the same thing for this one and the same thing for this one. So you have 3 ones that are isolated and occur as a size zone of 1. Now let's look at this number here. So the gray level intensity 3 occurs as a size zone of 3 once. So you have 1, 2, 3. It's connected here, and there are no other 3s in the grayscale image. So the gray level intensity 3 occurs as a size zone of 3 once. So that's how this matrix is made. You do the same thing for 4. So the gray level intensity 4 is connected as a pair of 5 once. So here you have, so 4, it goes this way. And then you have an isolated 1 because there's no 4 in the connecting neighborhood, and so you have the 1 here. And so what you've done in this simple matrix is that you have information regarding the gray level intensities. You have information about how they are connected, and you have information about how many times are they connected in that fashion. So you've got these three sets of information that were not possible before in the histogram representation. And so when we talk about the addresses we had the challenges we had highlighted, the first was how do we incorporate grayscale images? And so the gray level size zone matrix gives us the immediate technique. It is an immediate technique that can allow us to incorporate this grayscale information. And the spatial information is nothing but the connectivity of pixels that we are capturing in this case. So although this method that I've shown you right now is in 2D, we can calculate the same gray level size zone matrix for a 3D image. And that's what we're going to do now. We're going to apply the same technique to the porous media rocks. So here's a sand pack that I had shown you before. Here's the histogram we saw. And here's what the GLSZM looks like. So on this axis, on the x-axis, you have your gray level intensities. On your y-axis, you have the size zones or the connectivity. And this axis shows how connected they are. I just want to clarify that both the log scale and the z-axis are the same thing. I just have a color representation here. So the way you would read this GLSZM now is exactly how you read it before. The gray level, suppose 25, occurs as a size zone of 250 about 10 times. And so now, instead of just having a first order representation of histogram, which only has frequency and has gotten rid of all the spatial information, you now have a representation that can capture the spatial variation as well, which is a big jump from where we were before. Now, in terms of fieldstone, remember how we discussed that we had minerals that were not very obviously seen in here, the histogram. We can see these as peaks. So firstly, let me explain this. So the first peak here that you're seeing is the pore space that you see here. The pore space peak is here. Then you have the quartz peak. You have the quartz peak here. You have a quartz peak here, and this is the big quartz peak. What was missing here was the glauconite, which was the lighter minerals, and you now see that it stands out as a peak here as well. So this GLSZM gives us a way to, more distinctively visualize what are the heterogeneities in the rock in terms of the minerals. And so the information that we had previously lost because of the segmentation step can now be accounted for in such a representation, where we talk about the mineralogical heterogeneities in terms of connectivity, and we look at the connectivity of pores and minerals. So that's what is the advantage of this technique. The only thing we now have to look into is the microporous region. And so this was the ketone carbonate that we saw. This was the histogram. One was the pores, and that's what you see here, the normal pore space, the macropores. And the second one was the calcite that you see here. And the third one that I said is actually the sub-resolution porosity, but you really couldn't, say for sure that it was there, is now highlighted in the GLSZM as a very distinctive peak. So what we have now is a technique that can directly be applied to the grayscale images. It can directly show us what is the spatial variation of these gray level intensities in terms of connectivity. So you have the mineralogical heterogeneities covered, you have the microporous regions also covered as a part of these texture analysis technique. So what we had before is the traditional way was to go from raw microcity images to segmented images and flow simulation. What we can do now is we branch off from here, have a GLSZM representation, and from here we calculate the proxies to porosity and permeability. So instead of actually calculating them on segmented images, we can calculate some statistics of this map, which could be proxies to porosity and permeability. And so that's the new workflow. Now what we are doing is we directly go raw microcity images, GLSZM, and then the statistics. So what are these proxies to porosity and permeability that we've identified? So here's the GLSZM for an example, and we've identified a statistic which is called as low gray level emphasis. Just as the name suggests, it emphasizes everything that has a low gray level. So all your pore space would be emphasized. It doesn't care whether the pore space is highly connected, like the connectivity is high, or is it like really low connected. It would capture everything. And because your porosity looks, here we're looking at total porosity, so it looks at all the connected and disconnected porosity, so you would want to capture this entire area. And the way this is calculated is that here's your GLSZM matrix, and every value in this matrix is divided by the square of the gray level intensity, which means that a smaller gray level intensity in the denominator will give you a higher value for the low gray level emphasis. So all of these get emphasized over this, and that's how we treat it as a proxy to the permeability, because you're emphasizing everything that belongs to the pore space. Yeah, that's just the definitions. When it comes to permeability, what we are looking at is how connected this pore space is. And we want the pore space to be connected. We want a large connectivity to be seen. And that's why it's called large area, low gray level. So it's still looking at the low gray levels, but only those that are connected to a great extent. And so what that means is we would probably be looking at emphasizing only this region that has high connectivity, and not these regions that are just, you know, specks of low gray levels that you can see. And the way that's emphasized is that instead of just having the gray level intensities in the denominator, now you're multiplying every element here by the square of the connectivity. So now suddenly what you would see is that all of this gets emphasized very significantly, and all the low gray levels, they are suppressed. And so now we have two statistics that we've identified: the low gray level emphasis, we have abbreviated it as LGE, proxy to the porosity, and then we have LALE, which is proxy to the permeability. So let's sum up what we have done till now. The reason why we started the study was to address the challenge of using the raw microcity images directly for the digital rock analysis. And we wanted to capture the lost information that of the rock texture, which relates to mineralogical heterogeneity, connectivity of pores, and the microporous region. And we want this whole thing could be summed up as capturing the spatial variation that was initially lost. Oops. Yep. And how did we approach this? We approached this using a texture analysis technique for porous media rocks, and that was the gray level size zone matrix, which measures the spatial connectivity of the gray level intensities. We also found two statistics called the low gray level emphasis and the large area low gray level emphasis, which were treated as proxies to porosity and permeability. Having these two things in perspective, what can we do? We can then investigate the pore-scale REVs directly using the raw microcity images and compare it to what happens with the conventional methods. So the first thing that I'll tell you is what do we mean by a deterministic REV, and what do we mean by statistical REV? Now, the first point that I had mentioned is an REV is dependent on the property that you're investigating. So you will have a different property, different REV porosity, you'll have a different REV for permeability. Now, in this case, we are looking at both deterministic and statistical REV. The deterministic REV is inferred by choosing a small cube at the center of the sample. You calculate the porosity for that, and then you grow it to the full sample size, and at every step you calculate your porosity or whatever property you're calculating. And that looks like this graph here. So on your x-axis you have the small cube that was grown until the image size, which is 300 cube in this case, the full image size. So you go all the way from 10 cubed, 50 cubed, 100 cubed, all the way to 300, and you have the porosity. It's a normalized porosity, but let's look at it as a porosity on the y-axis. And so as you grow, what you see is that there's a large fluctuation in your porosity, and it tapers and it plateaus. And that's what you want to see. This is what the deterministic REV or the DREV gives you. Now, the thing that the deterministic REV doesn't capture is if we take these small 50 cube, say suppose, and we move it around the whole sample, what happens then? Do we get a different value? And that's why we need a statistical REV. And that takes the small cube, moves it all the way around, and then we calculate how much is the variation. And we do that for all these window sizes. And so as a result, you see these bars here, the error bars. These bars show how much variation do you have for that particular window size when you move it around. And we quantify it by using coefficient of variation, which is the standard deviation divided by the mean for all the window sizes. And there is a criteria that was introduced by Corbett and Jensen, who said if you want to assume that you have reached homogeneity or the REV scale, that is when your coefficient of variation is between 0 and 0.5. So that's what our criteria should be. And we have chosen it to be 0.1 for this study to be more on the conservative side. So what are we going to infer here is one, the grayscale REV or the GREV, and from the GLSZM representations that we got from the microcity images. And then we get the REV from the segmented images. And we do that for both porosity and permeability and their proxies. So let's look at what this gives us. This is a sand pack that we had previously discussed. And what we're comparing now is the LGE and porosity. So these are proxies. LGE is a proxy to porosity. And what you're seeing here is a graph that shows the deterministic REV and the statistical REV. Everything in blue. So the blue here shows the values we have got from the grayscale analysis, and the red shows the conventional method of using segmentation. So one thing that is that we can see is the trends are captured, and that's very important. And when we try and estimate what the deterministic grayscale REV is based on the blue part, that is our LGE, and we have the segmented volume, we see that the DREVs are same. And this is being verified by literature that used similar REVs, they used similar rock samples. And the same thing we did for the statistical GREVs. We took the coefficient of variation of 0.1, and we see when does this variation reach the threshold of 0.1. And that occurs at 105 voxels for the case of the grayscale, and 140 for the segmented image. We do the same for permeability, and again we see that the blue, which is the grayscale, follows the similar trend as the red one, which is the permeability. And the DREV in this case, again, we find it around 200, which is the deterministic, the one that grows from the center. And the statistical REVs here are around 295 voxels and 262 voxels. In the case of fieldstone, the porosity, we again see similar trends, and the DREV sort of tapers down here somewhere around this region, around 460 voxels. And this is again verified in literature what the values were. Now, in the case of statistical REVs, it's surprising that we see the coefficient of variation reach the 0.1 threshold quite early and not needing to reach this big, volume or the size of the sample. What about permeability? Now, permeability in this case doesn't seem to have REV. The reason for that is the if you look at the blue one, which represents the grayscale, the ones that are coming from this and the GLSZM, you see that both for this and the red one, the permeability, there's still an upward increasing trend. You don't really see much of the stability, and so we don't have an REV in that case for that sample size. If you considered a bigger sample, we probably would have reached an REV. That's something that we need to investigate once we have a bigger sample size. But for this sample size at this resolution, that's the result we get. And again, we measured the statistical REV and GREV, and so that was at 160 and 240 voxels respectively. With the ketone carbonate, we again have the trends that we expected. We did see a match with the trends, and you see the plateau reach around 200 voxels for both raw and segmented images and their proxies and porosity that we used. This is also verified with literature, and with in terms of statistical REVs, we find that's reached around 315 for the grayscale, which is the blue one, and 345 for the segmented one. For the ketone carbonate, again, the permeabilities sort of have the same trend, although on a different scale. And this was again reached around 400. The deterministic REV was reached around 400 voxels. The statistical REV, on the other hand, you realize that there's a lot of difference between the grayscale based and the permeability based of the segmented images. One of the main reasons that this happens is, one, we've ignored the sub-resolution porosity in the segmented images because there wasn't a way to resolve them at that resolution. That could be one reason, and also it could be permeability approximations that we've used. Right, so that's how the REV results look like. And the last part was about how fast is computing the proxies based on the GLSZM directly from the raw grayscale images. We did all the computations on an Intel computer, so it has a 3.2 gigahertz workstation and about 256 GB memory. The entire deterministic GREV analysis, which means going from that tiny cube all the way to this big 500 cube sample, took only 4.6 minutes. Whereas the permeability calculations for every step took about 242 minutes. So if you look at that big gap, it's already 53 times faster, the GLSZM approach. And this graph here shows for every window size, how much time would a GLSZM calculation take and how much time a permeability calculation take. So there's already a stark difference. You can see that it goes exponentially. If you had to, for example, if you had to do 10 voxel cubed images and you had to calculate permeability, the values just multiply exponentially. And so the GLSZM method, although not an substitute for segmentation analysis, it does give you a first step approach as to how would you go about looking at these images, the features that are not identified, and gives you a preliminary result which can be used as a foundation, and then you can analyze the segmented images. So just summarizing what we learned today is that we started off by this need to address the challenge of using raw microcity images for digital rock analysis. And we wanted to do that because we saw that we lost information based on the rock texture once we segmented to a binary image. We were losing mineralogical heterogeneity. There was ambiguity in connectivity, of course, and especially the microporous regions that were not really clearly visible from the histogram visualization. And so losing the spatial information was a concern. Additionally, for an REV analysis, we needed to make sure that this is not very time consuming and not very computationally intensive. So that's what our motivation was. And we started off by addressing this by using texture analysis, which we have seen has had a lot of success in disciplines like medical, remote sensing, and seismic images. And we have applied the gray level size zone matrix to measure the spatial connectivity of the gray level intensities. We've then identified two proxies, which are GLSZM statistics, as proxies to porosity and permeability. And using all of that, we have compared and inferred what the pore-scale REVs would be. And that's what summarizes the topic of grayscale representative elementary volumes and how we take this innovative approach of textual analysis to infer the REVs. You can read through the detailed conclusion. This again summarizes what I've just told you. And the way forward is doing a very thorough sensitivity analysis on how the noise, the reconstruction algorithm, and the image resolution affects the proxies that we've just mentioned and the GLSZM analysis. And another thing to really strengthen this analysis, which is right now very image-based, is to add physics-based approaches and link these statistics to actual petrophysical properties and alleviate the need for the proxies, develop benchmarks. And we can do that by the use of percolation theory or fractal dimensions, and this is currently the work in progress. As for where you can use the GLSZM technique, and on the top of my head, I can think of seismic imaging, is when you really need to look at the fracture connectivity in 3D. This GLSZM statistics can look at what intensities represent the fractures, and then you can study the connectivity and characterize these fractures using that. So I would just like to end the talk by thanking all of you who attended. I really appreciate the time that you've spent being here and listening to me. Also like to thank the Australian Society of Exploration Geophysics for giving me this opportunity, for Todd, Lauren, and Partha for organizing all of this. Special thanks to my supervisors, Payman Moshtagimi, Klaus, and Ryan. It's been a great pleasure working with all of you, and this whole research has been a product of the work that I've done. And we've had two collaborators on this piece of work. One is Stuart Walsh, who is at Monash, and Joost, who is a person from cancer research. And we took their help, his help, to particularly implement the code we were trying to look at. And all the Matrix team members. So this is a research group that I was working with during my PhD. And most importantly, the Amalia and Priya, who run the Tari microcity facility, because without them, I didn't have the images, and without the images, I didn't have my PhD. So thank you. Happy to take any questions. Yeah, if anyone has any.
Yeah, a very nice talk. Let's see if we have any questions popping up in the Q&A. Oh, there's one already, I see. Oh, that's just thanking you for a great talk. But, I do have, while we're waiting, when you're doing the X-ray,
Yeah.
sorry, it's easier to say than micro CT.
Yeah.
Do you pressurize? Do you the rock, or is what you're doing right now? Is it at just normal temperatures and pressures?
Yep,
I don't know
yep.
what your lab can do.
Yeah, I mean, well, I have not personally dealt with high pressure systems, but I know I have colleagues who, in my PhD friends, who are doing, high pressure, I guess, experiments, and so they often have to image their samples once they're fractured. And yeah, we do have facilities in our microcity, lab that can image after the high pressure has been applied to the rock samples, if I'm correct. Yeah, but I don't deal with that, so I think I'm not the best person to answer that question. Yeah.
Okay. Yep. But yeah, it'd be just interesting. And there's another, somebody else popped in. How does the reconstruction procedure affect the histogram?
Right. So yeah, I mean, I think that, let me just take it back to the, yeah, that's a long way. Yeah, thank you for asking that question. If you all see, there is, we have a lot of these grayscale intensities, and when we have a reconstruction algorithm that does not account for these high density minerals, what then happens is that the entire histogram just squeezes to a very small portion of your gray level intensity. And if we do not apply image processing techniques, you would see that you don't really capture any variation. All you see is a dark space, and you see that white speck mineral. If I can better explain that, let me just read, right?
Yep.
Yep, okay, so let me show what happens. So this is how the actual histogram looks like of the sand pack that I just showed you. This is what was on the presentation, and this is what we actually get. And the reason why this happens is that all of the space is taken by, or it's given to these minerals that are really high, have a high density. And if we do not account for this, we often end up with such a reconstruction, such a histogram, which we cannot really see there's any variation in here. This is just literally two lines. And this happens when the reconstruction does not account for the minerals. Now, if the reconstruction did account for the minerals, this is how it would look like. So this is done with two different reconstruction softwares, one that didn't account for and one that did. So that makes a huge difference, because this translates to your GLSZM. And if you cannot see this variation, you're really not capturing anything in the GLSZM, and hence the whole process is it doesn't give you the information that you think it should. Yeah.
And let's see. And we've got another question. In addition to pressure cells, we also use temperature, chemical, and mechanical load cells to mimic reservoir conditions at hydrochemical, thermomechanical loads. Pretty similar to my question, I think. So but going in more detail. So do you,
Right.
is there, you know, in UNSW, will you be able to kind of include that along with the X-ray technology?
Well, I think that's a question for the microcity people who will probably be listening to the talk. If yeah, I'm not sure who asked me the question, but if you can send me an email, I can forward it to the relevant people at UNSW who will be better able to answer your question. Yeah.
Yep. And someone did send off from PM to all panelists. I would add that the method presented here, that the method can be applied to high pressure and high temperature images, which is good. So, you know, my question is, you know, like you have your lab set up. So in other words, would actually have to have some kind of chamber that this subject would be inside when you blasted it for X-rays. And so, yeah, yep, kind of neat.
Yeah.
Okay. Let's wait a little bit more, see if we have any more questions. There's quite a few comments about great talk. We'll wait a few more and see. Well, I don't, okay, well, and then the only issue is that the quality of high pressure images is commonly lower than the images shown here. And thus the grayscale might not be as accurate. That's from Paiman Masagumi, I guess is
Yeah, he's my supervisor.
I was going to say that sounds like, yep.
Yeah, so I think if the question was, can we apply this technique to high pressure cells? Yes, we can definitely apply the techniques. It's about what information is retained and seen in the microcity images that we want to extract. So if the quality of the images aren't as great and distinctive features aren't seen, then the GLSZM method might not be the best to be applied in that case. Yeah, I think I read the question as, can we do the high pressure imaging at UNSW? Yeah.
Yep. Pretty neat. Okay. Yeah, it's definitely at least a way to not destroy your samples while you're trying to figure things out.
Yeah.
And, you know, as long as you feel safe with, you know, with the X-rays bouncing all over the place, everything's good. Okay. Yeah, which I'm sure everything is checked pretty carefully there. Just a joke. All right, so if we don't have any more questions.
So yeah, I think Maxim, yep.
Then we'll just wait one more sec and see. But then I think we can thank you for a great talk. And we'll go for the next one. One more. Russell says, thanks for a great presentation. So
yeah, thank you.
You bet.
Okay.
All right. So we will get this out onto the web, and there will be quite a few. I think, like I say, there might be some more people will be thinking of questions. So I think they know how to contact you. So it should be all good. All right.
Yep.
So,
yeah, I think that should be fine. I don't think I need my email here, I guess. Yeah.
All right.
Yeah.
So we'll let you go off and relax now, and everybody else get back to work.
Yep.
Hey.
Great. Thank you. Thank you, Joe. Yeah. Thanks, Soren.
Bye, everyone.
Bye-bye.